Jesse, we need to cook. Here we have solution A, which is 100 milliliters of 9% hydrogen peroxide. You can make this by taking 30% hydrogen peroxide, measuring out 30 milliliters of it, and then adding deionized water until you get to 100 milliliters, leaving you with solution A.
This is solution B. It is a acidified 0.2 molar potassium iodide solution. The solution contains 10 milliliters of 1 molar sulfuric acid, 4.3 grams of potassium iodide. All of this is diluted to 100 milliliters with deionized water.
This
is crack.
Solution C, our starch solution that will be used as an indicator in the reaction. To make this, we take 90 milliliters of deionized water and bring it to a temperature of 100 degrees Celsius. At this point, you can add 0.1 grams of Vitic starch to the solution, 1.5 grams of malonic acid, and 0.4 grams of manganese sulfate monohydrate. The entire solution is diluted to 100 milliliters using deionized water.
At this point now we're going to add solution A and B together. We're going to let them stir. After they're done stirring, we'll add solution C, at which point the oscillating reaction will occur, and it'll go for about 5 minutes or so. The major variable in this reaction is the iodide concentration. With a low iodide concentration, it will cause the production of iodide. When you have a high concentration of iodide, it will cause a consumption of iodide. And this will oscillate back and forth, which causes the color changes.
What was inside of this entire reaction? Solution A, we had a hydrogen peroxide mixture. Solution B, we had a potassium iodate and sulfuric acid mixture, and solution C was a starch, malonic acid, and magnesium sulfate monohydrate mixture. Of course, we could write this entire reaction out, but all that's important from these three solutions is that the starch is used as the indicator, and the magnesium sulfate monohydrate is used as the catalyst to get the reaction going.
This is the intermediate reaction that occurs. So basically you have these two reactions that are occurring, and these basically be summed up as the overall process that happens. Basically you have iodate that reacts with hydrogen peroxide to form hypoiodous acid, oxygen, and water. Then you come down here to reaction 2, where hypoiodous acid reacts with malonic acid to form iodo-malonic acid and water. Reaction 1 can be broken down to the radical and non-radical processes, and these processes will oscillate between each other, and that will cause the color changes to occur.
So we have two processes, this non-radical and radical. These both have their own set of reactions. They're fairly similar. The big difference being is the non-radical consumes iodide versus the radical does not require any iodide. Since the beginning of the reaction doesn't have any iodide available, the radical process will kick in. And in fact, at any time during the reaction, to determine which process is dominant, you look at the iodide concentration. If iodide is present, non-radical kicks in. If it's not present, the radical will be kicking in. So we start with the radical. The radical is an extremely fast process. It produces hypoiodous acid faster than equation 2 of the entire reaction can consume. Because of this, this acid builds up and combines with hydrogen peroxide to form iodide. This iodide combines with other iodides to form iodine. This is yellow in solution as it begins to build up, and that's where we see the solution turn yellow, darker yellow, as the iodine concentration increases from this radical process.
Iodine reacts with iodide in solution to form triiodide. Triiodide will react with starch to form the dark blue complex. As more of the blue complex builds up, the darker and darker it gets. So, at this point, there's enough iodide in solution to start to end the radical process and to start the non-radical process. This is because the non-radical process uses iodide. Now, as iodide is being used, it is going to stop the production of iodine. And when you stop the production of iodine, guess what happens? Yellow color goes down. Now, as there's less iodine, there's also less iodide. That means there's less triiodide formed, less starch, less blue coloring. Blue color goes down. As the colors are going down, guess what? Clear color goes up.
As we left off, the non-radical is consuming the iodide. Eventually, you consume all of the iodide that's available in solution, and the radical process will kick in again. The radical process will produce iodide that will kick off the non-radical process and stop the radical, and then the non-radical will consume it, consume, produce. And here you can see this is an oscillating reaction between the non-radical and the radical process of the reaction. So let's see if we can put some colors here from what's happening in the solution. Again, we start off on the radical process, no iodide concentration in solution. Radical process kicks in, iodide, we get yellow. Iodine, and iodine form to triiodide, which combines with starch for the blue complex, and we get blue. Non-radical kicks in, iodide is consumed, yellow decreases until we get down to the radical process, clear, and the whole process continues again. So we go clear, yellow, blue, clear, yellow, blue, clear, yellow, blue, clear, yellow, blue, clear, back and forth between the non-radical and radical. And eventually, either the iodide will be used up entirely or the malonic acid will be used up, and the entire reaction will just stop, and we'll be left with this brown mixture of iodine. Why you should listen. Let's think of some real-world examples of oscillating reactions. Let's say you want to have a baby. It's in your stomach, and of course you're going to start contracting. When you contract, your body is going to release oxytocin. What does oxytocin do? It causes you to contract. Contracting releases more oxytocin. Boom, oscillating reaction between oxytocin and contraction, causing your baby to be born, and when that's done, the reaction stops. Your body loves oscillating reactions. Why shouldn't you?
Let's say you want to cut off your arm. The process of cutting off your arm will cause a drop in blood pressure. This drop in blood pressure will be sensed by your heart, and your heart will start beating faster. This will an attempt to bring your blood pressure back up, but it will end up spewing out more blood till you die. Maybe your body doesn't love oscillating reactions as much, but for the most part, they're pretty good.
Now you should know how to do the Briggs-Rauscher oscillating reaction given the materials.
So now that you know how the Briggs-Rauscher oscillating reaction works, if someone comes up to you and asks you, hey, how does it work? You can tell them that it is an oscillating reaction between the radical and non-radical process.
We'll use the Vidic starch as an indicator.
So you do have a plan. Yes, science!